Hello children, once again welcome back to Physics with Sanoop, Healing Medical Aspirations. Now let's discuss PYQ of NEET from the chapter Rotational Motion. See, two objects of masses 10 kg and 20 kg respectively are connected to the two ends of a rigid rod of length 10 meter with the negligible mass. The distance of the center of mass of the system from the 10 kg mass is. See, the easiest way to find this is if you want to find the distance of the center of mass from 10 kg, you have to choose the position of the 10 kg as the origin. Okay. Then the x-coordinate of the center of mass means that will be the distance from the origin, or it will be the distance from 10 kg. Okay, now we have this is the formula for the position of the center of mass, or x-coordinate of the center of mass, if the two objects are supposed to be on the x-coordinates. Okay, and see, we have chosen the position of 10 kg as the origin because we have to find the distance of the center of mass from 10 kg. Okay, now see, m1 that is 10 kg but x1 equal to 0, and m2 that is 20 kg and x2 is equal to the length of the rod and it is 10 meter. Okay, and in the denominator we will have 10 plus 20, that is equal to 30. So 200 divided by 30, or 20 by 3 meter. Okay, 20 by 3 meter. A wheel has angular acceleration of 3 radians per second square and an initial angular velocity of 2 radians per second. In a time of 2 seconds, it has rotated through an angle. Okay, see, initial angular velocity is given, angular acceleration is given, time is also given. We have to find the angular displacement theta. Okay, so you have to use the equation which is similar to S equal to ut plus half at square. Okay, and here we will have theta equal to omega 0 t plus half alpha t square. Omega 0 is given as 2 and t equal to 2 seconds again. Okay, half alpha is 3 and t square means 2 square. Okay, here we have a 2 and this 2 can be cancelled. Then here we have 3 into 2, that is 6, 2 into 2, that is 4. 6 plus 4, that is equal to 10 radian. Okay, 10 radian, this one. Okay, now let's see what we have next. A wheel of radius 1 meter rolls forward half a revolution on a horizontal ground. The magnitude of the displacement of the point of the wheel initially in contact with the ground. See, initially this point is in contact with the ground. After half a revolution, this will be on the top, and it must have covered a horizontal displacement of pi r. So this is pi r and this is 2r diameter. Now see, this distance we have to find out. Okay, this one, right? Now see, consider this right triangle. Consider this right triangle. Okay, this is pi r and this is 2r. So by Pythagoras theorem, see, this will be under root pi r square plus 2r square. Okay, what is common? R, that we can take outside. Okay, and see, if we take the common factor outside, r outside, then under root pi square plus 2 square. Okay, that is pi square plus 4, and r is given as 1 meter. R is, radius is 1 meter. Okay, so it will be pi square plus 4 under root pi square plus 4. Okay, now let's see what we have next. What is the linear velocity if angular velocity is given and position vector is also given in component form? So linear velocity v equal to omega cross r. Omega cross r. Okay, so we have to form this determinant and evaluate it. Okay, suppose we are evaluating this determinant along the first row. Okay, take this element I cap. Okay. Now I cap, we have to eliminate the row and the column containing that particular element. So it will be minus 4 into 6, that is minus 24, and minus 6 into 1, that is minus 6. Minus 24 minus 6. Okay, minus 24 plus 6. So it will be minus 18 I cap. Okay, If see this we have to take positive and next element j we have to take negative. Okay, now see in this case we will have to eliminate the column and the row containing that particular element j. Okay, so 3 into 6 that is 18, 5 into 1 that is 5, 18 minus 5 that is 13. Okay, and there will be minus j, minus 13j we have. Okay, now next that is k, we have to eliminate the row and the column containing that particular elements. Okay, k cap, what remains? 3 into minus 6 that is minus 18, 5 into minus 4 that is minus 20. So minus 18 minus minus 20, minus 18 plus 20. Okay, that is plus 2k. So minus 18 I cap minus 13 j cap plus 2k cap, that is the linear velocity in vector form or component form, let us say. A solid cylinder of mass 2 kg and radius 4 cm is rotating about its axis at the center at a rate of 3 rpm. Okay, the torque required to stop after 2 pi revolutions is, see in each revolution it will turn through 2 pi and there are 2 pi revolutions. So the total angular displacement will be 2 pi times 2 pi or 4 pi square. So theta will be 4 pi square. Okay, yeah. See, this is, suppose finally the angular velocity is omega and final kinetic energy will be half I omega square. Initially it is at rest, so initial kinetic energy is 0. Final kinetic energy minus initial kinetic energy is the change in kinetic energy and it is equal to work done. In rotational mechanics, work done equals torque into angular displacement. Okay, see we have to find out the torque. See here it is a solid cylinder. Moment of inertia is mr square by 2, half moment of inertia mr square by 2 and omega is 2 pi into frequency, and frequency it is given as 3 rpm, 3 revolutions per minute. So frequency will be 3 divided by 60, 3 by 60. So 2 pi and frequency is 3 by 60. So that is omega whole square, means omega square, half I omega square. That is the change in kinetic energy equals work done, means torque into angular displacement. I have told you, the angle described in each revolution is 2 pi and such 2 pi revolutions. So 2 pi times 2 pi. Okay, so n is or angular displacement is 2 pi times 2 pi tau. Okay, now see we have to find this torque. Okay, this is 4 pi square. Okay, here we have 4 pi square and here we have 4 pi square, that can be cancelled, and this 2 and this 2 can be cancelled. Okay, and see here we have a 20 square, means it is 400. Okay, and on the and in the numerator we have 16 into 10 raised to minus 4. Okay, 16 into 10 raised minus 4. Here 400 into 2, that is 800. Okay, now see this, when this 100 is taken to the numerator, it will be 10 raised to minus 2. So it is 10 raised to minus 6. Then 16 by 8, that will be 2. So 2 into 10 raised to minus 6 Newton meter. 2 into 10 raised to minus 6 Newton meter. Okay. A rope is wound around a hollow cylinder of mass 3 kg and radius 40 centimeter. So its moment of inertia will be same as that of a ring and it is mr square. Mass is 3 kg and radius 0.4. So it will be 0.48 moment of inertia. Okay, what is the angular acceleration of the cylinder if the rope is pulled with a force of 30 Newton? Okay, so torque tau equal to force into perpendicular distance. Here it is equal to the radius. Force is 30 Newton and radius is 0.4. So it will be 12 Newton meter. We have to find the angular acceleration, that is torque by moment of inertia. So 12 divided by 0.48 and it is equal to 25 radians per second square. Here it is the angular acceleration, 25 radians per second square. Okay, force is given in component form. Position vector is also given in component form, the value of alpha, because see in the expression for force, its x component is alpha. Okay, that's a variable, it's not given, that we have, it's an unknown rather than variable, it is an unknown that we have to find out. Okay, the value of alpha for which the angular momentum about the origin is conserved. Conserved, angular momentum conserved. In order to conserve angular momentum, torque must be 0. So, how do we find the torque? Tau equal to R cross F. Okay, and here is the, we will find torque here. Okay, right, R cross F. Actually, we have to find alpha. Okay, now what we will do now, see, we will find the, see, torque should be 0. Torque 0 means all the components of the torque must be 0. X component of the torque should be 0. Y component of the torque should be 0. Z component of the torque should be 0. We have to evaluate or find out only the value of alpha. So we have to take only the, see, only the component which contains alpha. Okay, now alpha is here. Let's take the Z component or K component. So when we take this K, we have to eliminate the row and column containing that K. So the Z component of the torque will be 2 into 3, that is 6. And this is minus 6 alpha, 6 minus 6 alpha. It will be 6 plus alpha. See, Z component of the torque will be 6 plus 6 alpha. This is equal to 0. Okay, this is 2 into 3, that is 6. And this is minus 6 alpha. 6 minus 6 alpha, that is 6 plus 6 alpha. This is the Z component of the torque. Okay, that should be 0. Means alpha should be minus 1. Then only we will get this one equal to 0. Okay. Actually, you need not find all, you need not completely evaluate this R cross F. Means we have to find out only the value of alpha. For that, you have to find out only the Z component of the torque. Now children, let's see the next question. A solid cylinder of mass 50 kg and radius 0.5 meter is free to rotate about the horizontal axis. A massless string is wound round the cylinder with one end attached to it and the other hanging freely. Tension in the string required to produce an angular acceleration of 2 revolutions per second square. Usually, the angular acceleration is expressed in radians per second square. But here it is expressed in revolutions per second square. 2 revolutions per second square. See, in each revolution, angle described is 2 pi radian. So, in 2 revolutions, the angle described will be 2 into 2 pi means 4 pi radian. So, 2 revolutions per second square means it will be 4 pi radians per second square. Okay, so we have alpha equals 4 pi radians per second square. As it is a solid cylinder, its moment of inertia is mr square by 2. Mass is given 50 kg and radius is half meter. So, moment of inertia is 50 by 8. Okay, now suppose the tension in the string is capital F. This is the case. See, this is the side view, means as you view the cylinder from one side, see, this will be the case. And this is the tension in the string, capital F. Okay, the perpendicular distance from the axis is capital R. So the torque will be force into perpendicular distance, means tau we can write Fr, and it is equal to I alpha. So F, that we have to find out. Okay, so that will be I alpha divided by R. Okay, so this implies force will be I alpha divided by R. See, the moment of inertia we have 50 by 8. Okay, and alpha we have got 4 pi and radius is 0.5. Okay, this 0.5 into 8, that will be 4, and this 4 can be cancelled, it will be ultimately 50 pi. Okay, so 50 pi means it will be 157. Okay children, let's see what we have next. Okay, this is a beautiful question. A rod PQ of mass m and length L is hinged at NP. The rod is kept horizontal by a massless string tied to the point Q as shown in figure. When the string is cut, the angular acceleration of the rod is. See, the rod is hinged at this point. Okay, say when we cut this string, see, it will rotate under the effect of the weight. See, the torque due to the weight of the rod will be, see, this is the axis. Okay, from the axis to the line along which the weight is acting, the perpendicular distance is L by 2, and so the torque will be tau equal to mgL by 2. As the rod is rotating about this axis, passing through its one of its ends and perpendicular to its length, its moment of inertia will be ml square by 3. Okay, so tau equal to mgL by 2 and I moment of inertia ml square by 3. So alpha will be tau by I. So mgL by 2 divided by ml square by 3. So it is 3g by 2l. 3g divided by 2l. This is the correct option. So okay, this is a beautiful question. Okay, now see in linear mechanics or in see Newton's laws of motion or in work energy and power. See, suppose two bodies are moving. Okay, two bodies of masses, say m1 moving with velocity u1, another body of mass m2 moving with velocity u2. They collide, and after collision they stick together and move together with a common velocity, say v. Then there will be some, see, loss of kinetic energy. And that loss of kinetic energy, children please listen, half, then half, okay, loss of kinetic energy is half, okay, then m1 m2 divided by m1 plus m2, okay, and u1 minus u2 whole square. Okay, now see, suppose say capacitor is charged to C1, charged to voltage V1, another capacitor C2 charged to voltage V2. These two are connected together in parallel. They will attain a common voltage. The loss of energy delta U, loss of energy delta U, half C1 C2 by C1 plus C2. Then V1 minus V2 whole square, where V1 and V2 are not velocities, voltages, V1 and V2. Okay, means this form, okay, this form is very important. Here we have two rigid bodies with the moments of inertia, say I1 and I2. And they were rotating with the angular velocities omega 1 and omega 2 independently. Body of moment of inertia I1 is rotating with angular velocity omega 1. Another body of moment of inertia I2 is rotating with angular velocity omega 2. Here we have two circular discs. Now suppose I have taken this second disc and gently placed over the first. After some time they will attain a common angular velocity. There will be some energy loss, and that energy loss also will have the same form. Okay, and it is being given by half I1 I2 by I1 plus I2 into omega 1 minus omega 2 whole square. Okay, so this is here we have see, it is given as IB and IT, IB and IT. Okay, a circular disc of moment of inertia IT is rotating in a horizontal plane about its symmetry axis with a constant angular speed omega I. Another disc of moment of inertia IB is dropped coaxially onto the rotating disc. Means the second disc was initially at rest. Omega 2 is 0. Okay, so you can put this omega 2 and omega I will be, see, omega 1 will be equal to omega I. So this will be, that is very simple, half IB IT divided by IB plus IT. Okay, so this must be the correct option. A tube of length L is filled completely with an incompressible liquid of mass capital M and closed at both ends. The tube is then rotated in a horizontal plane about one of its ends with a uniform angular velocity omega. The force exerted by the liquid at the other ends is, okay. Now see, mass is distributed uniformly, okay, and mass per unit length, okay, that is lambda, represented by lambda, it is equal to m by L. Okay, now consider a small element of length dx, okay, at a distance x from the axis. See, at a distance x from the axis I have taken a small element and its length is dx. Mass per unit length is lambda. So mass of an element whose length is dx will be lambda dx. And what is lambda? It is m by L. Lambda dx will be m by L into dx. So this much is the mass of this small element. As the tube rotates about this fixed axis, that element will be moving in a circle. Whenever a particle is moving in a circle, there must be an unbalanced force, a resultant force directed towards the center. Suppose the liquid on the left side of this element exerts a force like this, and the liquid on the right side of that element exerts a force like this. Resultant force must be towards the center. So the force acting from left to right, okay, that is F, and the force acting from right to left must be more stronger, F plus dF, because then only the resultant force will be directed towards the center. Okay, so the resultant force, that is dF, because see, along this direction F and in the opposite direction dF. Okay, F plus dF. So the resultant force will be dF, right? And that provides the centripetal force. See, this much is the mass of the element, m. Next we have to take the radius of the circle in which the element is moving, that is x, mr omega square. Okay, so that much is the force acting on an element at a distance x. See, we have to find the force on all such elements from x equal to 0 to x equal to L. Okay, that will give you the resultant force, capital F, integral dF, m by L omega square x dx, to be evaluated from 0 to L. See, in which m omega square L is constant, that we can take outside, and when x is integrated we will get x square by 2. Okay, when it is evaluated from 0 to L, we will get L square minus 0 square divided by 2. So ml omega square by 2 ultimately. ml omega square by 2. Now let's see what we have next. Two bodies have their moments of inertia I and 2I respectively about their axis of rotation. If their kinetic energies of rotation are equal, then their angular momenta will be in the ratio. See, this is linear momentum in terms of mass and translational kinetic energy. See, corresponding relation in rotational motion, that is angular momentum L equal to under root 2 into moment of inertia into rotational kinetic energy, E with the suffix R. Here we have two bodies with equal kinetic energy, rotational kinetic energy, but their moments of inertia are different. Which one will have greater angular momentum, or we have to find the ratio of the angular momentum. See, we have two bodies. For both the bodies, this ER is the same and 2 is also same. So let us say angular momentum directly proportional to the moment of inertia. So L1 by L2 will be root of I1 by I2, and that will be root of I by 2I or 1 by root 2. Okay, so it is 1 is to root 2. Okay, now let's see what we have next. A wheel having moment of inertia 2 kilogram meter square about its vertical axis rotates at the rate of 60 rpm about this axis. See, frequency is given as 60 rpm, 60 revolutions per minute, or 60 revolutions in 60 seconds. So 1 revolution per second, or it is 1 hertz. And angular velocity will be 2 pi into frequency, so it is 2 pi into 1 or 2 pi radians per second. Okay, and the torque which can stop the wheel's rotation means the final angular velocity is 0. Okay, and it is to be done, or the wheel is to be brought to rest in 1 minute, means the time is 60 seconds. Alpha, we have delta omega by delta t, angular acceleration. Final angular velocity is 0, initial angular velocity is 2 pi, and that change takes place in 60 seconds. So the angular deceleration is minus pi by 30. Okay, tau equal to I alpha, and moment of inertia it is given as 2 kilogram meter square. So 2 into pi by 30, that is pi by 15 Newton meter. Pi by 15 Newton meter. Okay. A thin circular ring of mass capital M and radius r is rotating about its axis with a constant angular velocity omega. Initially only the ring is rotating. Okay. Now 4 objects each of mass m are kept gently to the opposite ends of 2 perpendicular diameters. Okay. Then what would be the final angular velocity? Initially only the ring is rotating. So the initial moment of inertia will be that of the ring, that is mr square, and angular velocity omega. So initial angular momentum will be mr square omega. Finally, there are 4 point objects kept on the ring. So the moment of inertia will be moment of inertia of the ring plus moments of inertia of these 2 point objects. See, the moment of inertia of a point object is mass into square of its perpendicular distance from axis. So the moment of inertia of each point object will be mr square. Such 4 objects are there. So total moment of inertia of these 4 point objects will be 4 mr square. And the moment of inertia of the ring will be capital M into r square. So finally, the total moment of inertia, this is the moment of inertia of the ring, and this is the moment of inertia of the 4 point objects. So this is the total moment of inertia and final angular velocity omega dash. So omega dash will be m omega divided by capital M plus 4m, m omega divided by capital M plus 4m. This is very simple, but it is a typical question. Many times same or similar questions appeared in this NEET question paper. So you have to understand this. A particle of mass m equal to 5 units is moving with the uniform speed v equal to 3 root 2 in the XOY plane along the line y equal to x plus 4. Okay, y equal to x plus 4. So the particle is moving along that line. Can you draw that line? Of course. Okay, so see that line, you can find the point where that line cuts the y-axis. How do you get that point? Put x equal to 0. When you put x equal to 0, you will get y equal to 4. Means the line will be cutting the y-axis at y equal to 4. Okay, so this is x-axis, this is x-axis, and this is y-axis. Okay, so y equal to 4, this point, that is a point on the straight line. Where do that line cuts the x-axis? How do you get that? Put y equal to 0. When you put y equal to 0, you will get x plus 4 equal to 0. Then x equal to minus 4. That is the point at which the line cuts the x-axis. Okay, this is positive x-axis and this is negative x-axis. So this is the point, this is another point on the line. So we have got 2 points. So simply join these 2 points, you will get the required line. Okay, the particle is moving along this line. So its linear momentum is acting along this line. We have to find the perpendicular distance from the origin to that line. Okay, so this broken line is the perpendicular distance, broken line. Now children, we have this right triangle here, no? We have a right triangle here. Okay, and see this angle is 45 degree, this angle is also 45. Okay, because see this is 4 units and this is 4 units, so this must be 45 and this must be 45. Okay, now see this angle, see this we have, see this one. Okay, this one we have 90 degree, this is 45, this is 45. So it is an isosceles right angled triangle. Which one? This one, an isosceles right angled triangle in which this is the hypotenuse. Okay, and it is equal to 4 units. Okay, so this will be, this is 4 by root 2 and this is also 4 by root 2. So 4 by root 2 is the perpendicular distance. Okay, 4 by root 2 is the perpendicular distance from the origin to the line along which the particle is moving, or to the line along which the linear momentum is acting. Okay, now let us find the angular momentum, that is P means mass into velocity. Linear momentum, mass is 5 units and velocity is 3 root 2. And the lever arm, that is the perpendicular distance that we have got 4 by root 2. This root 2 and root 2 we can cancel. See what remains, 5 into 3, that is 15 into 4, it will be 60 units. Okay. Now children, we have the equation of the straight line along which the particle is moving, that is given as y equal to x plus 4. Y equal to x plus 4. It can also be written as, see, take this y to the right, you will get x minus y plus 4 equal to 0. Okay, x minus y plus 4 equal to 0. If you have studied mathematics, you must be knowing that if this is the equation of a straight line, and if you want to find the perpendicular distance from say x1 y1 to x1 y1 to this line, what would be that perpendicular distance? X1 minus y1 plus 4 divided by root of 1 square plus minus 1 square. Okay, but here we have to find the perpendicular distance from origin. Means here we have to put 0, here also you have to put 0. So in the numerator only 4 remains, and in the denominator there will be root of 1 square plus minus 1 square, 1 square plus minus 1 square. So you will get 4 by root 2. Or perpendicular distance you can find either by using this one or like this you can find. However you find the perpendicular distance, you will get the angular momentum as 60 units. Okay. Now see the next question, the ratio of the radius of gyration of a solid sphere of mass capital M and radius r about its own axis to radius of gyration of a thin hollow sphere of same mass and radius. Okay, we have a solid sphere and a hollow sphere. See, moment of inertia is mk1 square, that is solid sphere, 2 by 5 mr square, and mk2 square, that is hollow sphere, 2 by 3 mr square. So k1 by k2 whole square will be, if we divide these two, we will get 3 by 5. So k1 by k2 will be root of 3 by 5, or let us say root 3 is to root 5. So this will be the correct option, root 3 is to root 5. From a circular ring of mass capital M and radius capital R, an arc corresponding to 90 degree sector is removed. See, if we consider this ring into 4 identical parts, see the moment of inertia about this axis, that is mr square, okay, and all the 4 quarters are identical, okay, and the moment of inertia of each quarter will be mr square by 4. Okay, now we have see, here there is 1, okay, here there is 2, and this is 3. So 3 parts. Okay, and the total moment of inertia will be 3 by 4 mr square, 3 by 4 mr square. And here it is given that k times mr square means k should be 3 by 4. Okay, so this is 3 by 4. Now 2 discs, same question we have discussed earlier. Okay, the loss of kinetic energy will be half. Okay, we have this formula I1 I2 divided by I1 plus I2, and here we have 2 identical discs, each of moment of inertia capital I. Okay, so this will be I square by 2I, or it will be I by 2. So I by 4 omega 1 minus omega 2 whole square. Okay. Now from a disc of radius capital R and mass M, a circular hole of diameter capital R. Diameter capital R means radius R by 2. See, from a disc of radius capital R, another disc of radius R by 2 is removed. Okay, like this. What is the moment of inertia of the remaining part of the disc about a perpendicular axis passing through the center? Okay. Now see, mass is directly proportional to area. See, the area of this removed part will be 1/4 of the total area. So if capital M is the mass of the original disc, okay, original disc capital M, then the mass of this removed part will be m by 4. Okay. Now see, the moment of inertia of the remaining part, moment of inertia of the remaining part is the moment of inertia of the original disc minus moment of inertia of the removed disc. What is the moment of inertia of the original disc? Let it be I1. The moment of inertia of the removed smaller disc, let it be I2. So the moment of inertia of the remaining part will be I1 minus I2. Okay. I1 See the moment of inertia of the original disk, that is mr square by 2, mr square by 2. And moment of inertia of the removed part means this smaller disk. Okay, about this axis, Okay, see moment of inertia of a disk about an axis. See, this is the moment of inertia of a disk about an axis, normal to its plane and passing through its center. It is mr square by 2. And here is the axis passing through the rim and normal to its plane. Okay, let it be capital I. Okay, so by parallel axis theorem, I equal to ICM plus MA square. ICM is mr square by 2 and MA is R. So see here A equal to R. Okay, so this will be I equal to, this ICM is mr square divided by 2 plus mr square. Okay, so the moment of inertia about this axis will be 3 by 2 mr square. Moment of inertia of a disk about an axis passing through the rim, through the edge and normal to its plane. That is 3 by 2 mr square. 3 by 2 mr square. Now see, but here the removed disk is of mass m by 4. So 3 by 2 instead of m we will have to put m by 4. 3 by 2 m by 4 and the radius is r by 2, not r. Okay, so 3 by 2 instead of mass we have to put m by 4 and for radius we have to put r by 2. Okay, so this will be, here we have r by 2 whole square means it is r by 4 into m by 4, that is mr square by 16. Yeah, mr square by 16. So 3 mr square by 32. Okay, 3 mr square by 32. So here we will have to subtract mr square by 2 minus 3 mr square by 32. Okay, mr square by 2 is common. When it is taken out, the first term will be 1 and the second term will be 3 by 16. 1 minus 3 by 16 will be 13 by 16. Okay, so it will be 13 mr square by 32, 13 mr square by 32. 13 mr square by 32. Okay, now let us see what we have next. Moment of inertia of the system, identical spherical shells. Okay, this is the axis. See, the axis is a diameter of the first shell. So its moment of inertia will be 2 by 3 mr square. And the axis is a tangent of the second and third shell. Okay, moment of inertia about a tangent will be 2 by 3 mr square plus mr square. Okay, see moment of inertia, this is the shell. Okay, and we want to find the moment of inertia about this tangent. We have to apply the parallel axis theorem. This is the axis about which we have to find out the moment of inertia. Consider an axis parallel to the given axis and passing through the center of mass. That will be a diameter. So this is I with the suffix em. Okay, and this distance a equal to r. So moment of inertia I, see this I will be equal to ICM plus MA square. ICM means this one, that is 2 by 3 mr square plus MA is r, so it will be mr square, and this is equal to 5 by 3 mr square. 5 by 3 mr square. So moment of inertia of the second disk about the given axis is 5 by 3 mr square. Moment of inertia of the third disk about the given axis is also 5 by 3 mr square. Total moment of inertia will be I1 plus I2 plus I3. Okay, so that will be, here we have 5 by 3 plus 5 by 3, 10 by 3 plus 2 by 3, that is 12 by 3 or 4 mr square. Okay, 4 mr square. The moment of inertia of a thin uniform circular disk of radius r and mass m about an axis touching the disk at the perimeter and normal to the disk, means passing through the rim and perpendicular to its plane. See, this is an axis passing through the center of mass and this is a parallel axis. Okay, this moment of inertia we have to find out. Okay, so we have to use the parallel axis theorem, I equal to ICM plus MA square As this is a thin uniform circular disc, ICM is mr square by 2. So it will be 3 by 2 mr square. 3 by 2 mr square. Okay. The ratio of the radii of gyration of a circular disc about a tangential axis in the plane of the disc and of a circular ring of the same radius about a tangential axis in the plane of the ring. Okay. Now see, this is a disc. Okay. And see, moment of inertia about a diameter. See, moment of inertia about the central axis is mr square by 2. Then the moment of inertia about the diameter will be half of it, mr square by 4. Okay, and this is an axis parallel to the axis passing through the center of mass, ICM. Okay, and this is I. So I equal to ICM plus MA square. So mr square by 4 plus mr square, that will be 5 by 4 mr square. And for a ring, this ICM, about the diameter, it is mr square by 2, and about this axis, it will be 3 by 2 mr square. Okay, I1 by I2 will be, the I1 by I2 will be 5 by 4 into 2 by 3. Okay, that is 5 by 6. Okay, I equal to mk square, and k will be directly proportional to I. So k1 by k2 will be root of I1 by I2. So root 5 is to root 6. Root 5 is to root 6. Okay. Now let's see what we have next. A flywheel rotating about a fixed axis has a kinetic energy of 360 joule and its angular speed is given. Okay, we have to find the moment of inertia. See, the expression for rotational kinetic energy is E equal to half I omega square, and I will be 2E divided by omega square. Means it is 2 into 360 divided by 30 square. Okay, this 360 and 130 can be divided. So in the numerator we will get 12 into 2, and in the denominator there will be 30. So it is 24 by 30, and it is equal to 0.8 kilogram meter square. Okay. Now next question. See, a ring of mass m and radius r rotates about an axis passing through its center and perpendicular to its plane with the angular velocity omega. Its kinetic energy will be half I omega square, and moment of inertia is mr square. So it will be half mr square omega square. Half mr square omega square means this will be the correct option.